So carboxylic acid derivatives, that sounds general, but it actually has a very specific meaning. And that specific meaning is that through some type of action of water, so some type of hydrolysis, will produce a carboxylic acid. So if something can be hydrolyzed to a carboxylic acid, it then fits this generic definition of being called a carboxylic acid derivative. So there are numerous different functional groups that fit that description. The most common ones that we cover in chapter 21 are this type. So there are others, but the most common types that fit this description are these 5. So the first thing, as always, is to understand your structures in terms of functional groups. So those functional groups are acid halide, where this can be any halogen, an anhydride, an ester, an amide, and a nitrile. So we've mentioned all of those different functional groups at some point during the semester. They get grouped together in chapter 21 because they all fit this general definition that under some type of hydrolysis, they produce a carboxylic acid. So if you remember last week when we were emphasizing the carbon of the carboxylic acid, so this carbon comes from this carbon, this carbon, this carbon, that carbon, and the carbon of your nitrile. So it's this carbon of those functional groups that ultimately becomes the carbon of your carboxylic acid. So I put water in quotes because some of these functional groups are very reactive. You can just add water to them. The water in the air, the moisture in the air on a humid day can convert that functional group to a carboxylic acid. Other of those functional groups are much less reactive, and you have to heat them using acid or base to get the hydrolysis to occur. Doesn't matter, they all fall under this category of hydrolysis produces carboxylic acid, and that's what renders these functional groups as carboxylic acid derivatives. So if you can hear me and if you understand now the definition of what makes something a carboxylic acid derivative, type OK in the chat. All right. So the next consideration is these functional groups, or these molecules, are all members of different functional groups. Traditionally, every time we encounter a new functional group, we have to do the IUPAC naming. So this chapter requires you to be able to do 5 new and different IUPAC naming sequences. And what's very irritating is all 5 of those are completely unique. So one of the big parts of this chapter is nailing the IUPAC procedure for these different functional groups. So for an acid halide, they have the generic term of an alkanoyl halide. So if we look at a specific example, so the thing that defines an acid halide is having an alkyl group connected to a CO double bond connected to a halogen. And there'll be a recurring theme when we name these carboxylic acid derivatives that there will often be two or more parts to the name. So what we see here is if we're going to name this as an alkanoyl halide, these are our two different halves to that name. So we have to name the halogen. So the halogen in this case is a fluorine. So this would be an acid fluoride. So that would be one or half or one component of the name. We then have to handle the alkanoyl portion. So as always, that's based on number of carbons. So we use this term alkanoyl to connect that to what you know as the simplest IUPAC naming, which is an alkane. So if we're calling this an alkanoyl species, that shows you that we're in fact removing that E and adding OYL to the carbon numbered determined base name or root name. So 3 carbons is propane. So we would lose the E from propane. So we would have propan, and then we have to add the OYL. So this molecule would be propanoyl fluoride. So again, 2 components to this name. Basically, half of it is your halide, and half of it comes from the number of carbons in that chain. So last week when we were naming carboxylic acids, reminded you that it's vitally important that you remember to count the carbon of your functional group. That is also vitally important in this chapter. So you'll see there that we have our 3 carbons. Remembering to count the carbon of our functional group. In this case, it's the carbon of the carbonyl group that's part of your acid fluoride. So it's very easy, it's very tempting to have this mindset of, here's my acid fluoride. There are 2 carbons connected to my acid fluoride. Very popular but incorrect answer would be to call this ethanoyl fluoride. Most of the wrong answers when dealing with these names is when people are 1 carbon short. So always remember in these chapters, remember to count the carbon of your particular functional group. So a 3 carbon acid fluoride is propanoyl fluoride. In general, I am relatively generous or forgiving when it comes to IUPAC names. However, in this chapter and what will be exam 3, I will be unforgiving because the detail of these names for these 5 different functional groups are all slightly different. So if you called this propanoic fluoride, you would lose a point. Or if you called it fluoropropanyl or fluoropropanoyl, that's wrong. So it's important that you get the details of these IUPAC names correct. So for your acid halides, these are alkanoyl halides. So you name the halide fluorine. Fluorine here would be a fluoride, a Cl would be a chloride, and so on. Then the first half of the name, based on the number of carbons, with the ending OYL, but always remember to count the carbon of your functional group. So any issues with naming acid halides? Type no if you have no issues with that. Okay, so just as a reminder, when we're doing our carboxylic acid, these are alkanoic acids. So again, remembering to count the carbon, in this case of our carboxylic acid. So this would be derived from butane, but they are butanoic acid. That's what we talked about last week for the carboxylic acids. So again, vitally important to remember to count that carbon of your carboxylic acid. So that then brings us on to this functional group. So this functional group has an R group connected to a CO double bond connected to an O, connected to a CO double bond connected to an R. So that is the functional group anhydride. And these are named as alkanoic anhydrides. So for an anhydride, you sort of have 2 different halves. And so you have to know the carbon chain based name for the 2 different halves. And you will encounter 2 different versions. So the first version that we'll talk about is where the 2 halves are identical. So this is called a symmetric anhydride. In this case, both of those have 2 carbons. So in the case where the 2 groups are the same, you only need to say that once. So that would be ethanoic anhydride. So the defining structure of your anhydride requires those 2 substituents. So if you only list it once, or if you only list one of those substituents, it's assumed that they are both the same. That's kind of similar to what we did, for example, with ethers, right? So ethers must have an oxygen with 2 R group substituents. But if we then say ethyl ether, that implies that both of those substituents our 2-carbon. Similar thing here, if we just call this ethanoic anhydride, that implies that both of those substituents are derived from our 2-carbon ethanoic acid. So that's either called a simple anhydride or a symmetric anhydride. What you also need to be able to deal with is what we would call an unsymmetrical or a mixed anhydride. And that just means that R1 is not equal to R2. So these are different, these are mixed. This is an unsymmetrical anhydride. And in this case, you have to list both of those substituents. So 2-carbon was ethanoic, 3-carbon, so propane, propanoic. So now we're talking about an alkanoic anhydride. In this case, 2-carbon and 3-carbon, we would name this propanoic ethanoic anhydride. But you might say, well, if I've got 2 different substituents, therefore I've got 2 different alkanoic groups, how do I know which one to list first? This is an important point because I've written up there what would be the correct IUPAC name. One of the ways that we would list certain things in our IUPAC naming is alphabetically, right? Substituents normally get listed alphabetically. But you will notice that P is coming before E. And that's because here the 2 alkanoic parts are not being listed alphabetically, but they're being listed based on their priority. So this is priority like we did for assigning Z or E, priority like we did assigning R or S to chiral centers. You rank the priority of the 2 different substituents, and the higher priority substituent gets listed first. So propanoic comes before ethanoic because it has higher priority. So you'd say, this is carbon, this is carbon. Carbon connected to 2 oxygens and a carbon. Carbon connected to 2 oxygens to a carbon. Same, so keep going. This is a carbon connected to 3 hydrogens. This is a carbon connected to 2 hydrogens and a carbon. Therefore, this has higher priority than that. Propanoic gets listed first. Ethanoic gets listed second. So it's not, so the order entirely is based on priority. But remember that that priority is not necessarily based on number of carbons. For example, if this had a fluorine substituent here, then that substituent would have higher priority than that, and then this portion would get listed first. So for an anhydride, not only do you have to remember that it's alkanoic anhydride, but you have to list those 2 things in order of priority, with higher priority coming first. So that is a bit more involved or a bit more complicated. So anybody have any questions or issues about naming anhydrides? Type no if you have no questions. So next functional group we're talking about has a R group connected to a CO double bond, connected to an oxygen, connected to an R group. So this is the functional group ester. Esters are named as alkyl alkanoates. This alkyl portion is based on that particular R group. And then the ending OATE is telling you or denoting that it's an ester. And then our alkane is then based on those number of carbons. So for an ester, the two components of the name are what is the number of carbons, including the carbon of the CO double bond. And we also have an additional term that tells you what type of ester. Really, an ester, as you know, is the product of an alcohol and a carboxylic acid. So this is derived from your carboxylic acid. In this IUPAC naming might talk about the carboxylic acid derived component. So that would be this portion. And then this is going to be your alcohol derived portion. So it's an ester of a particular carboxylic acid, but then this R group tells you, defines what type of ester. Is it a methyl ester, an ethyl ester, and so on. So we had a molecule like this. So CO double bond connected to O, connected to R, that tells us it's some type of ester. So we would first start looking at this portion. So this is the type of ester, whereas this portion is the part derived from our carboxylic acid. So again, remembering to count the carbon of our functional group, we've got 3 carbons on this side, 2 carbons on that side. So this portion is defined by our IUPAC term alkyl. So 2 carbons there means we have ethyl. Then our 3 carbon sequence is our alkanoate. So this 3 carbons is propane. So basically this portion comes from there, and the ethyl portion is coming from there. So ethyl propanoate, a 2 carbon sequence connected to the oxygen, but a 3 carbon sequence including the carbon of the CO double bond. So it's not random. When you have an ester, it's not random which one of those R groups you pick as your alkyl group. The alkyl portion of the name, the first part of the name, is the R group that's connected to the oxygen. That's defined or built in to the structure of the functional group. It's not about priority. It's not about alphabetic. It's not whether it's on the left or the right. It's the R group that is connected to the oxygen of your ester. And then it's this R group plus the carbon of the CO double bond that describes or is described in the alkanoate. So for an ester, there's 2 parts, alcohol-derived part, carboxylic acid-derived part. Those are defined by the structure. It's then a matter of defining correctly those 2 different components, putting them together to give you your ester name. Common places where people will go wrong with the esters is they will pick the wrong side, if you like, for the two different components of the names. Right, so the incorrect version there, somebody would say, well, this looks like 3 carbons here, propyl, 2 carbons, there it would be propyl ethanoate. So they basically switched the two different components that they were trying to name. Notice that that would then be both wrong. Another common wrong answer would be someone to say, recognize this as an ester, 2 carbons here, 2 carbons here. Therefore, I will wrongly call this ethyl ethanoate. It's tempting because you identify the functional group and then count the carbons, but you've got to remember to count the carbon of your functional group. So those are the IUPAC rules for naming normal esters. I'll talk about how you name cyclic esters in a moment. But if you fully understand the ester naming, type yes in the chat. Okay. So I'll do the cyclic ester later on. Let me just make a reminder here that I'm going to do that. Right. Hopefully I'll remember that if it's written up there. So we've done ester. So the next one we're going to look at is an R group connected to a CO double bond, connected to a nitrogen, connected to either hydrogens or R groups. So essentially an amine functionality connected to the carbon of a CO double bond. So if we start off with the simplest version, and we talk about an NH2 connected to that, we would categorize that as a primary amide. So if you think back to chapter 19, amines were categorized based on the number of carbon-containing substituents connected to the nitrogen. So our NH2 is a primary amine, 1 carbon connected to nitrogen. An amide, by definition, has to be connected to the carbon of a CO double bond. So that is a primary amide. A secondary amide would be an NHR. Tertiary amide would be NR2. So again, remember to count the carbon of your CO double bond. Here it counts if we're categorizing that as a primary amide. So for an amide, generically these are named as an alkanamide. So you can sort of see the two different parts of their names. So R group connected to a CO double bond connected to an NH2, you would recognize that as an amide. So I say amide, other people might call them amides, biologists call them peptides. right? So this is the linkage that connects your amino acids together to make peptides, dipeptides, polypeptides, enzymes, viruses, stuff like that. So for an amide, you're going to name it based on the number of carbons, remembering, of course, to count the carbon of your CO double bond. So this would be a 3-carbon sequence. So 3 carbons is propane. So propane, but drop the E because it's an alkanamide. And then simply you add the word amide, propanamide. So that's a 3-carbon amide. So that's the simplest way of naming it. If you then were to talk about a secondary amide, so now you have your amide linkage, but the nitrogen now has another alkyl substituent. So the naming of this is still, this is some type of propanamide, but it's a propanamide with a methyl substituent on the nitrogen. And in chapter 19, you learned how to handle substituted nitrogens. So we would then name this as N-methyl propanamide. So the N-methyl is telling you that the nitrogen has a methyl substituent, and it's still based on a 3-carbon amide. So this is nicely color-coded. Here's your propanamide, and this is the N-methyl, or the N-methylated version. So this is an N-methyl propanamide. If we had another substituent on the nitrogen, like another methyl, it would be NN-dimethyl propanamide. So again, notice that it's important that you can distinguish what carbons are being treated as substituents, what carbons are being counted in the base chain. Base chain is established by the structure of your functional group. Right? So if we're talking amides, amides must have an R group connected to a CO double bond connected to a nitrogen. That's what defines an amide. So that's what is determining this functional group name description. Anything else on the nitrogen is being treated as substituents. So this particular version, N-methyl propanamide. So it's not because P has higher priority than M. It's about what defines my functional group and what are my substituents. So again, notice very precisely that these are alkanamides. We've dropped the end E off the parent alkane name. So if you write PROPANEAMIDE, that would be a spelling error that you would then be docked for on exam 3. So it's kind of annoying, I understand, that each of these different functional groups have their own nuanced version of how exactly to write that IUPAC name. So that's how we handle amides. Again, later on, I'll do the cyclic version, but there's one more functional group we need to get to before we do the cyclic versions. So anyone have any problems naming amides? Type no if you have no problems. So the last functional group we're going to look at has the CN triple bond. Now this is different, structurally different to all of the other functional groups that we've addressed. In chapter 21, because all of the other functional groups that we've talked about in chapter 21 have been an R group connected to a CO double bond connected to something else. Here we're talking about an R group connected to a carbon connected to a nitrogen through a triple bond. Obviously this is different because it doesn't have a CO double bond. But the thing that joins all of these functional groups together in chapter 21 is their hydrolysis gives you a carboxylic acid, and nitrile fits that category. So the important thing, so this is called a nitrile. The IUPAC naming is to name it as an alkane nitrile. So if we do our specific example, you would see your R group connected to a carbon, triple bonded to a nitrogen, therefore it's a nitrile. As always, recurring theme, got to count the carbons or count the carbon of your functional group. So here we would have a 3 carbon containing nitrile. So 3 carbons gives you the propane, and then you just add the word nitrile. Propane nitrile. Kind of straightforward, but 2 important issues to note. Again, you have to avoid the temptation of saying, there's my nitrile, 2 carbons, therefore ethane nitrile. That's not correct. You must remember to count the carbon of your functional group. The other important aspect is notice that in this name, we've kept that E. So this is propane nitrile, and that E has been kept in the name. Notice that that's different when we talked about amides. If we had this amide, this would be propanamide, and you would notice that there is no E. So this is the detail that we'll be looking for when you're doing the IUPAC naming of these carboxylic acid derivatives. So you will, of course, say, well, that's annoying, that's stupid. Why do they do it that way? The answer is it's about preventing 2 vowels being consecutive or preventing 2 consonants being consecutive. So the fact that nitrile starts with an N, it means or requires that we keep the E in that name. Similarly, because amide starts with A, we then drop the E off the carbon base name. And the reason why you want to avoid, or IUPAC says that you must avoid 2 vowels or 2 consonants, is because of the way how it sounds when you say it. So verbally, it's more difficult to say if you don't obey that rules. So propanamide is easier to say than propaneamide. And propanenitrile is easier to say than propanenitrile. So that's the reason why they made those distinctions. Kind of annoying, kind of very detail driven, but it's also the last chapter of Organic 2. So they're really going to test your ability for attention to detail, in this case, spelling correctly your IUPAC names. So again, a lot of these names have two components. One is the carboxylic acid derived component, and the other is the functional group name. The rules are the rules, you just have to follow them, but always remember to count the carbon included in your functional group. It's very tempting to say, there's my functional group, this is my substituent, but that's not how it works, because that functional group includes one carbon. So traditionally, incorrect answers, if they've got the correct naming sequence, is because people are off by one carbon. So if you fully understand nitriles, and you also now understand why in some cases we keep the E, why in some cases we remove the E, type OK in the chat, and then we'll get to the cyclic versions. Okay, so you're probably thinking that's a lot to learn, or I guess this semester that's a lot that I will have to look up and answer correctly from my notes or Wikipedia or the textbook or some other place. But there's one extra additional level of complexity that we're going to talk about for some of these carboxylic acid derivatives, and that is how to handle their cyclic versions. And there are two important cyclic versions that you have to know about. So one is what I'm going to call a cyclic ester. So this is just some generic ring sequence, but the ester linkage is an integral part of that ring system. That's what we're calling a cyclic ester. So it's not a ring with an ester substituent. It's a ring where the ester linkage forms an integral part of that ring system. So a cyclic ester is called a lactone. So the word lactone means cyclic ester. And there are rules for naming lactones. So that's the first one we'll talk about. We just talked about rules for naming esters. Cyclic esters follow a completely different set of rules. So this would be an example of a ring system. The ester linkage is an integral part of that ring system. So we're going to name that as a lactone. So the rules for a lactone say that you name it as a hydroxyalkanoic acid lactone. So the logic for doing that, because sometimes we forget that all of the IUPAC naming is based in a purely systematic, logical way of naming molecules. And it comes from the understanding that an ester comes from a carboxylic acid plus water. So carboxylic acid plus alcohol gives you ester plus water. So we're talking about an ester, but we're really talking about a cyclic ester. So to make a cyclic ester, what we need is this group to be connected to that group. And then when they form your ester, those things are connected together. You get a cyclic ester. So what we're really saying is, if you're going to name a lactone, IUPAC says that you have to name it as the hydroxy substituted carboxylic acid that would react with itself to give you the corresponding cyclic ester. So you basically name this as this molecule, and then you add the word lactone. So this is the lactone of this molecule. So the easiest way is to number your carbons and then work backwards. So this is an ester made from one, two, three, four, five, that alcohol. So this oxygen becomes that oxygen of your alcohol, whereas this carbon and this oxygen are those. So this carboxylic acid with an alcohol substituent, if it reacted together, would ring close here and give this lactone. So this is annoying for you because to name this, you have to figure out how this would be made. So we call this retrosynthetic analysis. It's just alcohol and acid, but now they're in the same molecule, cyclides or intramolecular reaction, and then you have to name this. So you know from your carboxylic acid naming skills that this would be 5-hydroxy, remembering to count the correct carbons, pentanoic acid, so 5-hydroxy pentanoic acid, which makes this molecule 5-hydroxy pentanoic acid lactone. So that is how you would name that lactone. That's a lot of work. That's a lot of work to name a lactone because you have to work backwards, get the parent hydroxy substituted carboxylic acid, figure out what that is, then name it, and then after all of that, remember to add lactone to indicate that it is a lactone. So that's a lot of work to get to the correct IUPAC name. So anyone have any issues with that? Type no if you have no issues. So that was the first cyclic version. The second one is when you have a cyclic amide. So now the amide linkage is an integral part of that ring system. So a cyclic amide is called a lactam. So lactam means cyclic amide. The amide is an integral part of that ring system. So this is very analogous to the one we just did. So normally we'd do carboxylic acid and amine gives you amide plus water. If those are connected together, what we really need then is to figure out the carboxylic acid that then has an amine substituent also in that molecule. So again, I would encourage you, we actually do a specific example, to number your carbons. This is carbon number 1, carbon number 2, and then carbon number 3 is where your NH2 would be. So we're going now to an amino substituted carboxylic acid. So this particular one would be 3-amino propanoic acid. So 3-amino propanoic acid. So if we're going to name this molecule, that is 3-amino propanoic acid lactam. If this had substituents, and we had substituents here, you would then just follow your IUPAC naming rules that you got in chapter 19. So this could be an N-alkyl amino or 3N-alkyl amino propanoic acid lactam. So again, you got to work backwards, go from your carboxylic acid derivative, then to a carboxylic acid with a substituent, name this correctly, then add in the word lactam. So lactam for a cyclic amide, lactone for your cyclic ester. So that's already an hour just on the correct way to IUPAC name these carboxylic acid derivatives. So that's basically the first half of the recitation. So anyone have any questions or issues about the IUPAC naming rules for those functional groups? You type no if you have no issues, and then we'll move on to a different topic.